To enable robots to manipulate objects in remote settings, such as space operations, robots need to be able to register objects of interest within their environment. Often these manipulations involve articulating the objects, for example, turning the top of a valve to close it. Ideally, to register objects for manipulation, the robot needs to have an accurate representation of the location and state of these objects. For example, the pose of the valve and the angle of the handle. Unfortunately, existing automated methods for recognizing articulated objects lack robustness for use in mission-critical environments, and manual registration methods are burdensome for users. While some human-in-the-loop, semi-automated methods for registration have been proposed previously, they do not consider articulation and the corresponding impact to the object geometry. In this work, we propose a human-in-the-loop method for registering articulated objects, which combines semi-automated fitting with human-in-the-loop corrections. Specifically, our method attempts to automatically fit the model, pose, and articulation for user-selected points. Our method limits operator input to selecting points and providing corrections when the result of the semi-automated fitting is incorrect. Our method takes a 3D point cloud and a list of models as input. After a user selects a point, the system fits each candidate model and selects the best model based on a weighted residual from the fitting. If the model is incorrect, the user can cycle based on a sorted likelihood. If the pose or articulation is incorrect, the operator can provide relative corrections, after which the system can optionally refit the model. Our fitting extends the iterative closest point algorithm to enable the fitting of articulated models. Typically, the iterative closest point algorithm, or ICP, solves for the optimal rotation and translation that align two sets of corresponding points. Specifically, the algorithm alternates between calculating optimal transformations and calculating new correspondences using a nearest neighbor check. This same process can be used to localize known models in a point cloud by sampling the mesh as one set of points. Typically, the optimization step is solved in closed form using the singular value decomposition. To enable fitting articulations alongside the optimal rotation and translation, we instead modified the optimization step to use nonlinear fitting, which simultaneously estimates the optimal position, rotation, and articulation. The ICP algorithm is subject to local minima introduced by iteratively calculating correspondences between two sets of points. To minimize the chance of local minima, we use a random restarts procedure where the initial position, rotation, and articulation are randomized. We developed an open source implementation of our method. The implementation consists of a Python and C++ backend and a ROS front end. We leverage RViz for operator input and to visualize registered objects. Users are also given additional controls through a custom RViz panel. The fitting algorithm was developed in C++ and parallelizes the fitting of models through OpenMP. We conducted a 2x2 within subjects user study to assess our method. The study was designed to confirm the benefits of our semi-automated fitting and to explore two different input methods, a space mouse and interactive markers. The goal was for participants to register 5 objects on a task board, 3 of which had articulated handles. Participants were able to practice with each method for up to 10 minutes before beginning the trials. The 4 conditions were space mouse manual, interactive markers manual, space mouse with fitting, and interactive marker with fitting. Our study results showed that the semi-automated fitting resulted in a lower time on task compared to manual fitting. Our study also showed that the semi-automated method was easier to use, more useful, and had a lower task load compared to manual fitting. We also found that while all participants preferred the semi-automated fitting, not all participants preferred the refitting. Participants generally found the space mouse to have a lower ease of use and usability, but did not have a significant decrease in performance compared to interactive markers. We also constructed a situated example which demonstrates our method as part of an end-to-end object manipulation system. The task was to actuate a 1-inch ball valve which was initially opened to a partially closed configuration. First, the robot scanned the scene using a pre-programmed trajectory to collect an environment map. After the scene was displayed, the operator could fit the valve and then program the intended articulation. Finally, the robot would perform the manipulation. The robot could also optionally rescan the environment to confirm the final state of the object. In summary, we presented and evaluated a human-in-the-loop method for registering articulated object models, which combines semi-automated fitting with user corrections.